Hi, I'm going to go through the book Introduction to Commutative Algebra by Atiyah and MacDonald. I'm no expert for this topic, um, so I plan to go through it as slow as possible, and I will try to cover all the exercises in this book. I plan uh, to upload videos every 2 or 3 days, and in each video I will do uh, a sequence of exercises. I will mix the order and try to find some inner logic, uh, just as you can see in the first video. Mm, okay, so today I plan um, to give the first one to the prime spectrum, since it is the most interesting part of the chapter one. The prime spectrum of a ring. We always assume the ring is commutative with the identity element. And we also introduce the notation X to indicate the set of all the prime ideals of A. For now, X is just a set. In the first exercise, we will give X some topological structure. It's just the definition of the topology. So that's the purpose of this video. So let's begin. Uh, the we first give some definition, like for any subset E of A. Oops, E of A, we define the V of E as some subset of X, which includes all the prime ideals of A such that it contains E. So we just give some uh, take a collection of prime ideals which is bigger than some subset of A. And the first question is like, can we replace E, the subset E, by some other things like an ideal or the radical of the ideal, which can keep the V of them? The answer is yes, because it is something we need to prove. But this thing is in fact very interesting. So we will try to give some um, interesting proof, some a proof which includes more information. We first look at the fact we need to use to prove this. The first thing is like we all know E is a subset of A because A is generated by E, and A is also a subset of the radical of A. And we can see like a prime ideal contains a bigger subset must contains a smaller subset. So an easy direction for this equality is like the V of E must contain the V of A and the V of the radical of A. Well, this direction is almost trivial, but we can still make some conclusion for this fact, for this observation. We will call it the fact one. Like if E and F are two subsets of A, and E is contained by F, we'll have that VE must contains VF. In other words, take V is somehow order preserving, but you need to be careful because the order here is somehow a little bit subtle. We see the subset, the set of subsets of A has a order given by the inclusion, like this. But the order for the subset of X is a little bit different. We see VE is smaller than VF if VF is contained by VE. So this is the first one. And we also need to do the other direction, which means that we need to prove VA is contained by VE. VA contains VE, and V, the radical of A, is contains VA, which means that any prime ideal contains E, must contains A, must contains the radical of A. To prove this, we need some observation, in fact. What is A? A is, in fact, the intersection of all the ideal contains E. And what is the radical of A? The radical of A is, in fact, the intersection of all the prime ideal contains A. So if a prime ideal P contains E, then this prime ideal P is just an example of B here. If prime ideal P contains A, then the prime ideal P is just an example of this Q here. So we can give this, we can give the proof for the other direction. For any P contains E, because P is an example of this B, so it must contains A. And because P is an example of this Q, so it must contains the radical of A. So it's done because we can directly translate these two arrows as V of E is contained in V of A, and it is also contained in V of the radical of A. In fact, this is the fact 2 we use. But as you can see, like these two equality, these two identity, the A generated by E, this ideal is given by the intersection, and the radical of A is also given by the intersection of prime ideals. only this one is non-trivial, and this one is just the definition, in fact. So the solution for this question is, in fact, based on this factor, V is auto-preserving, and this factor, like the radical of A, is somehow the maximal element of a family of prime ideals respect to this order. We will see, I guess we will see this claim later, since it is the most important thing, most important part, I guess, for the prime spectrum. Okay, for the first one, we didn't see any topology, but for the second question, we can see something at least. We see we need to prove v of 0 equals x, or just translate into language of elements, whereas this one is equivalent to, like, for any prime ideal, zero belongs to P. This one is just trivial. And for the second one, we need to see for any prime ideal, one, the identity element is not an element of P. This one is also trivial. Otherwise, P is not a prime ideal. P is the ring A itself. So it is done. And we will see the meaning of this question later. But let's go through the third question and the fourth question. Okay. For this question, we need to prove, like, for any family of subsets of A. Any family means finite family or infinite family. We don't know the numbers. Maybe there are many, so many. We want to see the V of their union is equal to the intersection of V for each subset. Since we have nothing like this we can use, so we can the only method is go through the definition of the V. Take for any. Maybe one direction is somehow easier, since the union of EI must contain each EI. Then, since V is auto-preserving, so we will have the V of the union is contained by the V of EI for each I. So it must be contained by the intersection of all these EI, or VEI. This direction is somehow trivial because we have the property of auto-preserving. For the other one, for the other direction, we need to use some definition. For any prime ideal, P belongs to the intersection. Belongs to the intersection the algebraic subset. Okay, we need to see P is in fact contains all the EI. But the first step is because P belongs to the intersection, so P must belongs to VI for each I. And then by the definition, P contains each EI. Then this is equivalent to P contains the union of each EI. So P belongs to V of the union of EI. In fact, all these arrows here is if and only if, as you can see. So in fact, we don't need the first sentence. Let's just erase it. Okay, bingo, that's done. We have seen the intersection of any numbers of this kind of way of some set of A. And for the next question, we will see the union of two of them. As you can guess, for if we can prove this identity for the union of two, we can prove the same identity for the union of any finite number. So for the question 3, we have the intersection of any number. And for the question 4, we have the union of any finite number. So we can guess, we get some collections of closed subset of some topological space. That is the purpose of this exercise. For the question 4, well, we need to prove an identity, but maybe we can think about our order preserving argument, and we can first prove one direction, one simpler direction. First, with a very simple result about ideals is the product of two ideals is contained in the intersection of these two ideals. And the intersection, of course, is contained, belongs to both of them. Then, by the order preserving argument, we have the V of the product contains V of the intersection and contains V of A and V of B, both of them. So it contains V of A union with V of B. this direction is just the order receiving argument of V, so it is very simple. And then we need to prove the identity. Maybe a direct guess is the following claim. We need to prove the union of these two contains V of their product. To prove this, we just need the definition. Take any P belongs to the V of the product. We need to prove P belongs to either V of A or V of B. Let's just assume without loss of generality, like if P does not belongs to V of A, which means that there exists at least one element of the ideal A does not belongs to P. And then you can see for any element of B, they are the ideal. XY, the product belongs to the product of the ideals. So it must belong to the prime ideal P. However, X does not belong to P. So Y must belong to P by the definition of the prime ideal, which means that B is contained by P, or C. P is the element in V of V. So we are done. We want to look back for the four questions of this exercise. Let's see the meaning of the last three questions. The question 2, the second question, means that the collection of all this kind of V set includes the whole space X and also the empty set. The meaning of the third question means that the collection of this V subset is somehow closed with respect to the intersection of any numbers of this kind of V sets. And the third one means that it is closed with respect to the union of two of them. So this three means that the collection of all these V subset gives the collection of closed subset of a topological space. Which is, in fact, it is the Zariski topology. the prime spectrum. Mhm. But for the first question, we need to think it over. It says that uh, if we have a subset E of A, we in fact cannot distinguish uh, the by V like the E uh, with respect to the ideal generated by E and the radical of this ideal. So somehow, although V is auto-preserving, but it is not so faithful. And we can also say that the V of E, uh, as you can guess, is some closed subset of the spectrum. So the map, if you regard the map V as some map from the subset of the ring A to the subset of the prime spectrum, it is neither injective nor surjective. But you can still think how to make it a bijection. We just choose a subset of the set of all the subset of A and also a subset of the set of all the subsets of the spectrum and just take the radical ideal and the closest subsets, maybe we can get a bijection. And in fact, we have this kind of conclusion. I guess that is the most important thing for prime spectra. The new Snellen size, that is mm, the size, new Snellen size for prime spectrum. But it is totally different from the difficulty to prove the theorem is totally different from the helpless ones. Uh, his theorem mm, is for the maximum spectrum, which is somehow harder, much harder. Okay, to understand this theorem, we need to first understand the auto-preserving things, and we also need to understand the meaning of the bijection, because bijection somehow means that the map V has a inversion map, and the other two things is the closed subset we have um, talked before, and also the radical ideals. First, let's start with the radical ideals. There's a definition. Ideal A of the ring A is called radical. 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 If R of A equals to A. Usually, the R of A is somehow bigger, but for a radical ideal, they are just the same. Maybe the definition somehow is not so easy to use, but we can use equivalent ones. A is equal to the intersection of all the prime ideal contains A. This one is better, as we can see later. Okay, order preserving we have seen before. but I'm very willing to repeat the definitions of the two orders for two, maybe to, mm, let's see, maybe to set E and F as subsets of A. We see E is smaller than F if E is contained by F. And that is the order in the set of all the subsets of A. And the second thing is the order of the between subsets of the spectrum. We see that St are subsets of the spectrum of A. We see S is smaller than T if S is somehow contains T. A little bit different because in our mind, the order for the subset of a topological space is usually given by the inclusion of the open subset. And here, the ST is refers somehow to the closer subset. So the smaller of the closer subset, the bigger is complement as an open subset. So that is the reason why we define the order in this way. Okay, uh, we have explained what is order, what is the virtual ideals, what is the closed subsets. We also need to give the construction of the bijection. Maybe we can, to make it easier, we can restrict ourselves for E and F radical ideal to make it easier. And here we can also assume S and T are just two closed subsets. So don't need to mind about any other subsets. Okay, so for the proofs, we need to contract the the bijection, or maybe a pair of bijections. We have already had one of them, the V, which maps from the radical ideals or ideals of A to the closed subset of the spectrum of A. That is the first map, and we have discussed about this because the order preserving property. For the other one, I would like to use the very for historical reason. I use the letter I, capital I, for the other map. For any subset of the spectrum, define a map on it, map to the ideals, in fact the radical ideals. of A basis for here as is defined as intersection of all the elements or say all the prime ideals belongs to S, which is of course an ideal belongs to A. And one can easily say that the R of this ideal must be contained by the intersection of R of each P inside S. But the R of the prime ideal must equals to the prime ideal itself. So this one is in fact included in IS and and IS also contained in the radical. So we get IS is a radical ideal. Radical ideal. So that is a map, and we need to prove I is also a order processing map. Is somehow directly by the definition of that, because if S is contained by T, then by the property of intersection, the intersection of prime ideals belong to S must contain the intersection of prime ideals belongs to T. So this is IS, this is IT. So S contains IT. The second thing is we need to prove the V and I are pair of maps which is inversions for the other on the images, in fact, on between the closest subset of the spectrum and the radical ideals in A. So how can we prove this? Usually it is very hard because in fact we change the domain and the target, but we can use some trick, some very standard trick. Let's think about I V V V I V. Sorry, the composition of this maybe triangle. Let's see what's this. The claim is V I V equals to V I V I equals to I. This is just some standard argument. You can see it almost everywhere. There are some reasons for this kind of thing, but I will not talk about this today. Maybe I will talk about in the next video about the global connection and the closure operator. Okay, to say this to attend this scratch, we can use the second claim in this way. Let's look at any first look at any ideals. The ideals is of course smaller than itself, and by the order preserving argument, V of A is also smaller than V of A, and by the second claim, we have that claim of above, we will have A is smaller than I V of A for any ideal A. Okay, this is the first thing. We prove that the map IV, the composition of I and V, is somehow bigger than the identity map. And the second thing is, if we take any subset of the spectrum, we can do almost the similar things. We first take the this one, and when we map through I, and we move I to the other side, we will have V of I of S is smaller than S. So if we compose three of them, we will have what? We will have the composition of V and I and V. If you look at here, this by the associativity is equal to this. We first compose V and I at first, and then compose V. And by this inequality, we have this one is somehow smaller than V. This smaller means if we put any ideals here, the same ideal, this inequality holds. But if we look at the composition in this way, we can use this inequality, which means that this one is somehow bigger than V. So we have the composition of 3 is equal to just one of them. Similarly, we have the composition I first I, and then V, and then I equals to I. That is the proof of this claim. Okay, for the proof of Noish denizens, we only need to use the claim 3. Let's just copy it here. That is the only thing we need to use. As you can guess, that is the magic of the pair V and I. So we must have some general argument for this kind of thing, this kind of pairs. That is the global connections. We will see it in the next video. But here we can use this statement. This statement implies the image of I is just the image of I and the V composition because it is equals to the image of IVI. You can see this identity by, because you know the image of I must be contains the image of the composition I and V, and must contain the composition IVI. But IVI is just I, so the three images are just the same. Similarly, we have the image of V equals to the image of V and I equals to the image of V, I, V. That is the first corollary from the claim. The second one is the composition V and I are identity map on the image of V. And also the composition I and V is the identity map on the image of I. Then question, what is the image of V on the image of I? We have seen the image I mapped by V to where? We have seen it is just the image V. And the map I will map the image of V to image I. So combine these two together, we'll have V and I as I bijections, pair of bijections between the image of I and the image of V. This is just standard argument. And the next thing, we only need to prove the image of I is just all the set of all the radical ideals. Okay. And the image of V is all the closed subset in the spectrum. The second equality is somehow easier because that is the definition of the closed subset. We define any closed subset in the spectrum by the image of V, by the V of some ideal or some subset of the ring A. For the first one, we need some argument. First, the 2 is just obverse by the definition. For the first one, we can see one direction is easier because we have seen all IS are radical, which proves this direction. For the other direction, take any radical ideal. If A is radical, which means that A is equals to the intersection of uh, of the prime ideals containing A. This is what? This is the I of V of A, right? So so A must belongs to the image of I. It's done. That is proof. Okay, let's look at the next exercise. The last exercise is about the collection of closed subsets of the topology, and this one is about the basis. And the first question is this kind of subsets of the spectrum give us a basis. So we need to prove the collection of all this XA is a basis for the topology. Here, each XA is defined as the complement of VA, the closed subset of the circuit topology given by the prime ideals containing one single element A, and we want to show it is a basis. So, so in fact, we only need to show the following things. We need to show that for any prime ideal, which is a point in the spectrum, and any closed subset, well, you can use open subset, but since we have already defined our closed subset, F equals to, let's see, V of some ideal. You can directly choose a radial ideal, but I just write down an ideal such that P does not belong to this closed subset, which means that P is a point in the complement of F. The complement is an open subset. We need to show that for this pair, a point P and a closed subset F, we can find A such that P belongs to XA and XA is disjoint with F. In other words, the complement of XA VA is bigger, contains the closed subset F. Okay, it seems not so direct, but it is in fact very simple because you can focus on this condition. P is not a prime ideal in this closed subset, which means that this is our claim. And if we want to prove the claim, we need to find this small a, this element. And P is not a prime ideal in V, the ideal A, if and only if P does not contain A by definition. So which means that there is an element in A, and this element does not belong to P. What's the meaning of this? The meaning of this is A satisfies that P is an element of the open subset corresponding to A. We will call it basis open subsets. And the second thing is because A is an element of the ideal A, so V small a contains VA, which is F. So we have finished our proof. Well, the next two questions is not necessarily correct for any topological basis, but here we can see it is correct. They are correct. The first thing is about when this basic open set is empty. XA is empty, which means that there is no prime ideal, does not contain this element A, which means that for any prime ideal P, there is an element in it. And A is just equivalent to say that A belongs to the intersection of the prime ideal, so it belongs to the nilpotent radical of A, which is just equivalent to say A, this small element is nilpotent. Very simple. But maybe we can say a few words about this. Somehow we may notice that the definition for the prime spectrum is not so strict. It cannot distinguish elements, in fact. Like if two elements, if just one element is nilpotent, somehow takes the prime spectrum will taking the spectrum will lose this information. It cannot distinguish a nilpotent element and the zero. It may cause some trouble, but somehow it is much easier than maximum spectrum or algebraic variety. Okay, the next question. When XA equals to the whole space, it means that for any P, A is not an element of P. One can easily say that if A is a unit, this direction is of course correct from the condition A is a unit to A does not belong to any prime ideal. Otherwise, the P is not a prime ideal, P is the ring itself. So this direction is easy. And for the other direction, we just need to notice that if we assume A is not a unit, then ideal of A, which is not the ring itself. It must be contained by some maximal ideal. And the maximal ideal is, of course, a prime ideal. And then this observation will tell you M does not belong to XA, which is a contradiction. And by this, we get this direction. So it is also not hard, in fact, very simple. To prove this, we can directly use our Euler-Steiner test for prime spectrum, which is very direct. Since if we look at the complement of these two basic open sets, we will have the V of A equals to V of B. If and only if you map it by the bijection I, you will see of VA equals to I V of B, and take V and then take I, you will get the intersection of prime ideal which contains the element A. So it's the radical ideal of the ideal generated by A. For the right half side, it is the radical ideal of the ideal generated by B. So we're done. Okay, if you want to assume you do not know the Newton size, you will need to indeed prove this. You can still easily prove this, in fact, because let's assume this is unknown. Let me change it to another color. And we just want to prove from the very definition, very simple definition, VA equals to VB. What's the meaning of this? We know VA is the VR of A, and VB is VR of B, radical B. By the question 1 here. See, so this is for the proof of this, not for this direction, for the if direction. If RA equals to RB, we will have the two are equal. For the other direction, the thing is in fact simpler because the R of the radical of the prime ideal, the radical of the ideal generated by A is just the intersection of P belongs to VA. And because from this condition, we know VA equals to VB. So this is also the intersection of all the prime ideal of VB. This is the radical of the ideal generated by B. So we're done. Okay, for this one, to prove X is quasi-compact, firstly we need to figure out what we need to prove. We need to prove that we can fix our condition like X is covered by a family of open sets. We can also, since we know better about the closed subset, so we can equivalently try to prove, like if we have a family of closed subsets, directly choose the V of AI, such that each AI is an ideal. Fix this, and if X is covered by the complement of this closed subset, which is equivalent to say the intersection of the family of the closed subset is empty. We want to prove we can find a subfamily, find a subfamily such that the intersection of closed subset of this finite subfamily is already empty. This is what we want to prove. And to prove this, we only need the following observation. The intersection is empty, which means that the closed subset corresponding to the union or the summation of this family of ideals is empty. The two are equivalent by the intersection formula of the subset, this formula. And we can replace the union by the summation because we are working on the ideals. Okay. Then, what's the meaning of this? The meaning of this by this question. If and only if A is a unit, its corresponding basic open set is X, you can get some idea like this thing happens if and only if the identity element belongs to the summation ideal. In other words, we can find AI, such that AI in this. But the summation, it can be defined. It is well defined if only finite AI is non-zero. So we just take the non-zero AI denoted by J. Our finish is done. Our proof is done. B of the summation Bj is empty. Okay, this is a proof by the closed subset, but you may think, since we have already known information about the basic open set, we can use another way, like we consider we can consider the 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 spectrum, the total space is covered by a family of basic open set, and then we prove that only finite number of them can uh, has already covered the total space. But you will see the key point is still here. The summation is inside the finite summation. Otherwise, it is just meaningless. So this is a proof for the question 5. But for the question 6, the situation is almost similar. In fact, we can see if we take A is a unit, then XA is just the total space. So question 5 is just the special cases of question 6. But whatever, we can uh, prove them separately. Still use maybe as maybe this time let me use the basic open set, but you can also use the closed subset. We first claim if XA is covered by a family of basic open set, then we have a finite family such that XA is already covered by them. And how can we prove this claim? We just need to notice that XA is covered by this um, basic open set. The meaning of this sentence is like for any prime ideal does not contain A, it must belong to one of them. So it mustn't cover at least one of these AI. In other words, if we consider the ideal generated by all of these AI, it must contain A. So the sentence, this condition is equivalent to A belongs to belongs to the, let me see, belongs to the radical of the AI. This ideal. Why? Because because when we can directly still use the complement. The meaning of this is just the intersection of free AI is contained by VA. Okay, I betrayed my belief. Anyway, and then we can use things like we can use the map I or the order preserving property of the map I, or we can consider the equivalent. You can consider all the prime ideals. But anyway, we have R of A is contained in R of AI, and this is in fact equivalent to the argument here, since A must belongs to this thing, and if conversely, if A belongs to the radical ideal, then the ideal generated by A also belongs to the radical ideal, then the radical ideal of the ideal generated by A must be contained by this radical ideal. So they're equivalent. But if you are familiar with this thing, you can directly see these two sentences are just equivalent. Okay, if you get this, you can use the same argument. The meaning of the second sentence is like there must exists positive integer n such that the nth power of A belongs to the ideal generated by AI. And then this one is equivalent to say AA has the formula as a summation of elements from AI, from the ideal generated by AI. And to make this definition, to make this formula meaningful, we need to assume only finite xi is not zero, and we can find a family of I which is finite such that A has can be decomposed into the summation, and we are done. Okay, the first, these two questions is about the uh, basic open set, quasi compact, and the last one talks about when when is the open set quasi compact. The answer is it is quasi compact if and only if it is a union of a finite union of these basic open sets. Um, the only if part is somehow very simple. For if you firstly, you may notice that U is covered by let me see, for each x, let's see, we always use p, right? For any p belongs to U, we can find some x a p u such that each x a p u satisfies this condition. It is an open neighborhood of P, but it is also contained by U. It is this formula is correct because this XA is a family of a topological basis. So we have this. U is covered by a family of basic open sets, and by the summation, U is quasi compact, which means that U can be covered by a finite subset of U, where J is finite. Then we will have, we just have that U is covered by a finite union of basic open sets. So this is the only if part. The if part is also very simple. We can see like U is a finite union of P of a let me see, for xaj, and you need to remember each xaj is quasi compact, and a finite union of quasi compact subset will give you a quasi compact directly by the definition of quasi compact. You can take a finite cover for each xaj, and you take a union. Since since J is finite, so you will get a finite union, a finite covering of the whole total space U. So U is of course quasi-compact. It is done. We don't have much. I don't have any more things to say about this exercise, since it is just about quasi-compact. But you need to remember, usually a spectrum should not be Hausdorff, because T2 condition somehow is very strong. It is usually not correct. Okay. For the next exercise, this exercise talks about the at least T0. In fact, we usually cannot get T2. Sometimes we cannot expect T1, but this exercise shows that T0 is always correct. Let's firstly select the maybe the if part. If P is maximal, then we can see that the closed subset defined by P is this. Because it is maximal, P is the only prime ideal containing P. So this one is closed. Very simple. Conversely, if you want to prove if this set of one single point is closed, what we will have? There are many different ways. Maybe let's just use the definition. Let me think if it is possible. Yeah, it is possible. P is closed, so it must be equals to V of some A by the definition of closed subset. And then this one is equivalent to C. P is the only or because P is the only ideal containing A, but A is also but we know that the maximal element in VA it must be a maximal ideal. So P is of course a maximal ideal because it is the only element in this closed subset. Okay, for the next question, we consider about the closure of a one-point set. Firstly, we know P must be a point in this closed subset. So we have the closure must be contained in this VP. And secondly, conversely, if for any closed subset V of some A which contains P, which means that P containing this A, and we can see this is equivalent to, by the order preserving argument, this is equivalent to C. V of A must be contain V of P. This is correct for any closed subset containing P. So VP must be contained in the closure of P. Combine these two things together, you will have the closure of a point in the spectrum is equals to the closed subset defined by the prime ideal itself. We will see maybe in the next picture, like why this thing is correct. There is in fact a general statement from the theory of process, like if you have a pair of Galois connection, you will always have two operators in fact, and each of them defines some operator which will map a subset to the closure of this subset. So they are called a pair of closure operators. In fact, we have already seen them, but you can guess the composition of V and I and the composition of I and V at a certain closure operators. But the interesting part is to define them. You don't need any information about algebraic structures like rings, ideals. You only need the order. That is enough. That is the magic of Galois connections. Anyway, let's look back of this exercise. The question 3. If you have another point belongs to this closure, let's see what will happen. Since we already know the closure of a point is VP, so for this direction, for the only if part, we firstly get this thing Q belongs to V of P, and this is equivalent to P is contained by Q. Very simple. And because the first arrow is also by arrow, so we can directly write them down. Very simple, just by the definition. So you can see, because you can always because it is somehow very common, like one prime ideal is contained by the other one. The only prime ideals which does not contained by the other prime ideals are just maxima ideals. So that is abstraction for the prime spectrum to be T1, which is a very big abstraction, in fact. If my memory is correct, there was something about complete lattice in the exercise of Atiyah and MacDonald, and in that case you will see some different story, like we almost get a compact and Hausdorff space. Yeah. Okay. Let's don't waste time for something we have not met. Okay, this problem is we need to prove X is a T0 space, and there are many different ways, but equivalent with each other to speak about T0 space. I choose a very simple one, and you can prove by yourself. This one is equivalent to the definition in his hint, but this one is just simple, just simpler. We want to prove for any different 2 point, their closure is different. By the third question, we already seen, like let's first assume the closure of P is equal to the closure of Q. Then we can see like P is contained. P belongs to the closure of Q, and Q is also belongs to the closure of P. And by the third question, we know this is equivalent to C. P belongs to Q, and Q belongs to P. So P is equals to Q. P equals to Q. We are done.